Okay, in the previous class, we were discussing about the NVIC, nested vector interrupts, and I showed you how the ARM Cortex M4 responds to any interrupt and what are the steps taken by the microcontroller to complete any interrupt. Okay, and I also showed you about the modes in which different tasks actually are running, and then when an interrupt comes, how the stack is managed, how the stack pointer moves from one region to another region, how the data are stored in the temporary registers are stored in the stack registers. So these all we discussed in the last lecture. Okay, so now we are going to talk about the ARM Cortex M4 instruction set. First of all, let me tell you that ARM Cortex M4 has got total almost 200 instructions. Okay, and these instructions can be divided into 4 different groups. If you recall, 8085 has got 74 instructions. Similarly, here you have 203 instructions, and these instructions are divided into 4 different groups, 14 different groups. Remember, you don't have to by heart these 14 different groups, but in general, you can remember that there are 14 different groups, that's all. For example, instructions related to moving the data from the register or from the memory to register and registers between the registers and so. Arithmetic instructions are there to do arithmetic operations such as plus, minus, multiplication, division, modulus, and so on. Then we have logical instructions to perform operations like AND, or not, XOR, and so on. Then we have shifting and rotation instructions in which the single byte or single bit of a register can be moved in left direction or right direction, or shifted to one position, shifted to fifth position, and so on. Okay, so anyway, in future we will be covering almost all these instructions when we will be writing our own programs in C. You don't have to by heart these 14 instructions. Okay. Apart from that, we have 65 floating point unit related instructions. Okay, floating point unit, I told you there is a separate unit for floating points which actually handles all the instructions or all the programs which are related to floating point and all. So whenever you use floating point instructions like floating point, I believe you remember this kind of numbers are floating point. That means with a decimal point. Okay, so a separate section for that kind of variables and that kind of instructions are there, and 65 instructions are dedicated for floating point unit. So it has got a very big instruction set, and of course it can do very complicated mathematics.
So you are not presenting.
I'm not presenting.
Yes, so your presentation is not visible.
I
Also, sir, your
started.
voice is cracking.
Just don't worry.
Sir, you were presenting, but then you stopped.
Wait a second. I will present it again. Because now.
Yes, sir.
Is it okay?
Yes, sir.
Is it okay now?
Yes,
Okay.
sir, yes. Yes.
Is it visible now? PPT
Yes,
is
sir.
visible. Okay. And voice is cracking, you are saying. Now is it okay? Hello?
Sir, it was fine earlier also.
Okay. Is it still cracking? Someone was having some issues regarding that, right?
No, sir, not right now.
Okay. Done. So, okay. I was talking about this. So, I was talking about this slide. Okay. We discussed all the NVIC related things in the previous class. Apart from that, I was showing this PPT in which I told you that there are 203 instructions, okay, with ARM Cortex M4 instruction set. There are 14 different groups. These are the 14 different groups, okay, in which you have data moving related instructions, arithmetic, logical, shifting related, data conversion related, bit field processing related, and so on. So all these are there, but we are not going to talk about all these instructions right now. Later, when we'll be using our or writing our own program, these instructions will come automatically. Apart from that, there are 65 instructions which are dedicated for floating point unit, and I told you floating point numbers are numbers with decimal numbers. And there is a very beautiful mathematics how the computer actually handles these floating point numbers, because whenever we are talking about numbers, all these numbers in the microcontroller or in the memory are something like this, right? 2586. So these are hexadecimal numbers. So how any floating point number is converted to a hexadecimal number, there is a beautiful mathematics behind it. We will briefly discuss that part also. Okay, so length of data types. There are 4 categories of data types. When we say data types, we are talking about the variables we declare, for example, int, char, long, all those kind of data types. So anyway, there are 4 main categories of these data types. If we are using a 64-bit data, we will call it double word. Remember, word is the size of the microcontroller itself. For example, if we are using a 32-bit microprocessor, the word size will be 32-bit. 8085 used to use 8 bits, right? 8085 was an 8-bit microcontroller, right? Microprocessor. In that case, the word size will be 8-bit only. So remember, the word is nothing but the size of the microcontroller itself. Okay. So double word means 2 times of the word, so 64-bit. Okay. So 64-bit data are double word, or it will take 8 bytes. Next, 32-bit data are there, which are known as word, and 4 bytes. So whenever in future we will be saying word, remember it is a 32-bit data, or it is taking 4 bytes in the memory. Then of course 16-bit data are also there. We will call it half word, and it will take 2 bytes in the memory. And of course, last but not the least, 8-bit data is known as byte, and it will take 1 byte in the memory. Okay. Below this, for example, it is not possible that you use 4-bit data. It is not allowed. Okay. 2-bit data is not allowed. 8-bit is the smallest data that you can handle. And with ARM Cortex M4, in one time, you can use maximum 64-bit data. You will call it double word. Okay. There are data types which can use 64-bit data. Okay. So just for a reminder, if we say the size of int, what will be the size of int? Int for Cortex M4. Size of int.
4 bytes.
Size of int. Yeah,
4
it
bytes.
will be 32-bit. Okay, yeah, 4 byte. So remember, it is not necessary that the int will always be 32-bit. Again, I am giving you this information that int is nothing but the size of the processor itself. So suppose tomorrow if you are dealing with a 16-bit processor or 8-bit processor, int will be occupying that 8-bit only. Okay, int will represent 8-bit. Int will represent 8-bit for an 8-bit microcontroller or microprocessor. Similarly, int is 32-bit for a 32-bit mu-p or mu-c. Depends. So remember, this int is not a fixed size. Okay. Now, coming to a very important term called pipelining. You might have heard this term many a times before, right? Pipelining speeds up the instructions, and it actually makes the microcontroller or microprocessor more efficient. So what is pipelining? So this technique actually helped the ARM company to increase the speed of execution. So how can we simply understand this particular term pipelining? Okay, pipelining is nothing but a mechanism in RISC processor. RISC means reduced instruction set computer. Okay, reduced instruction set. So it has got small instruction set. Okay, so reduced instruction set computer is RISC. RISC processor uses to execute instructions. So using a pipelining, you can speed up the execution. This is the biggest advantage. Okay, this is the advantage. So what is pipelining and how we can understand it? There are so many different ways in which people have explained this particular term, and I am using my own way to explain it. And there are many other videos in YouTube which explains pipelining. Okay, suppose you went to a hotel and you checked in the hotel. There is a receptionist and you checked in, and she took 10 minutes to check your documents and check in all the detail. After that, after 5 minutes, after that, you ordered some food, and the same receptionist came to receive your order also. Okay. Then after that, she went to the kitchen and prepared the food for you, and she took 30 minutes for that. And later, after that, okay, when you are checking out or moving out of the hotel, she is the same person who gives back or cleans out the things and all. So she took 15 minutes for that. So indirectly, if you see here, this whole process of checking in a hotel, finishing at lunch or dinner, and coming out of the hotel, it will take almost 1 hour. So by that time, if suppose someone else is also waiting to order the food or get into the hotel, he will have to wait approximately 1 hour for the whole task because she is busy. She cannot attend this person. So he will have to wait for 1 hour to just order a food or check in also. So this process is inefficient. Yeah, it is inefficient because all the tasks or all the jobs are done by one person, or same resource is used to do all the tasks. So now this is an inefficient system. So what can be the solution here? The solution is, if you want to increase the speed of the system or the overall efficiency of the system, then you can divide the job, right? Divide the job among different workers. So what will happen? In that case, one person will be just taking note of the check-in, and by the time the second person will take the order, next person will go and prepare the order. So in this way, second person can move in after 10 minutes, and after 15 minutes, this person's order will be taken. So in this way, you can speed up the process. So how this same scenario can be applied to a microcontroller, that is the pipelining of microcontroller. So pipelining of jobs. So first of all, let us see how a non-pipelined system is doing its job or completing the job, and why it is inefficient. So we have time here, time taken to complete the job, and we have task here. Task means different jobs. Maybe when we say task, so suppose one instruction wants to add something, the second instruction wants to move the data, and the third instruction want to subtract the data, or so on. So there are many instructions which are coming to the microcontroller. Okay, so those are all different tasks. Okay, let us see here. So I have divided the time into different scales, like time T0, T1, T2, T3, T4, T5. Okay, so let us see here. So when you have a non-pipelined job, the task one will come, and time T0 will be taken, or it will take time T0 to fetch the instruction, right? Then after that, because you are not using pipelining, this task one will be decoded, then task one will be executed. So it took T0 to T2 to complete task one. Okay, remember here you have the task one. So fetch, decode, execute. It took this much time. Then after that, it will go for the task 2, fetch, decode, execute. Then task 3. So by the end of somewhere on task 5, you have just fetched the task 3. You have only fetched the task 3. It is very inefficient way because you are wasting a lot of time to complete the different tasks. So this is non-pipelined system. Let us look at a pipelined system. Okay, so that let us compare how efficiently we can manage different things. So in this case, of course, task 0, time t0 will be taken to fetch the task 1. But in the next time here, t0 to t1, fetching is going on, which is for task 2. At the same time, task 1 is decoded. So task 1 is decoded now here in this time. At the same time, task 2 is also fetched. Then task 1 is executed here. Okay, so task 1 is over by T2. But by that time, you see here task 2 is decoded. Okay, and task 3 is fetched. So now from here, from this time, you start seeing the advantage of pipeline system, because right now in one particular slot of time you are doing 3 different tasks. Okay, now the pipelining starts, or what we can say, we can see the efficiency of the pipeline system here. Now what happens? Task 1 is over, fetching, decoding, executing, done, right? So here task 2 has been fetched, task 2 decoded, task 2 executed. So task 3 fetched, task 3 decoded. By that time, task 4 is also fetched, and then task 4 is decoded, and here it will be executed. So now you see, even before reaching to T5, you have almost finished task 4. So what is the trade-off? For example, when you see this kind of system compared to the previous system, can you tell me? We are, of course, increasing the speed of the overall system, because in very short time you have completed more tasks. So speed is increased. Speed is increased because you are now able to perform multiple tasks in a short time period. Apart from that, one more important thing, in the beginning, this region, right? In this region, almost the pipeline and non-pipeline system are having the same efficiency. So the efficiency increases when the pipelining reaches to its maximum pipelining of the system. For example, if suppose someone asks you, can you tell me what is the size of pipelining in this particular system? Or how many stages are there in this pipeline? Anyone?
3.
Yeah, stages. So remember, this pipeline has got 3-stage pipeline. Okay, so 3-stage pipeline. This is known as 3-stage pipeline, because in one particular time you can do 3 different tasks. This is one way to see the pipelining, okay, or say stages. So speed is increased. But what is the trade-off? Whenever we say trade-off means, of course, whenever you are gaining something, then what you are losing at that time. So what is the disadvantage in, or what is the challenge to achieve this particular system? Anyone? Of course, speed is increasing, but what is the trade-off? To increase the speed, what we have paid for it?
More resources.
Right. So now we have to use more complex system, right? And we can say, or just like he said, more complex system, or we are using more resources. Okay, for example, in the hotel, when there was only one lady who was receiving the order, who was preparing the food and serving the person, everything. So in that time, there was only one person. So you have less resources, you have to pay less salary to that woman. But of course, to speed up the system, if you need more number of people, you will have to pay more salary. So you are using multiple resources, and at the same time, the system becomes more and more complex also. So this is the trade-off. Speed, of course, it is increasing, but complexity also increases, or we can say resource required for higher pipelining is also more higher. Okay, but of course, the market says go for the speed. So of course, more and more pipelining kind of approaches are utilized in modern microcontrollers. So this is pipelining. If suppose someone asks you in future what is pipelining, you can recall these particular examples. Okay.
Excuse me, sir.
Mm-hmm.
Sir, I had one doubt in that.
Mm-hmm.
Sir, like we are taking the same time for each task. Like for fetching task one, we are taking from 0 to T0
Mm-hmm.
and subsequent. Sir, what if there is a time difference between the fetching of task 2 and the
Right, right,
decoding of?
right, right. If you can recall the timeline, or sorry, timing diagram of 8085. Okay, just briefly, I'm telling you. Uh, there were three tasks which 8085 used to do, which is opcode fetch, right? Opcode fetch. If you recall this, right? Opcode fetch, memory read, and then memory write. These were all the tasks which 8085 used to do. And can you tell me how many cycles they used to take? Opcode fetch, how many cycles? Clock
40,
cycles? 4 T states or 4 clock cycles, right? Similarly, memory read,
3.
3 clocks. Why I am going back? Because these are all correlated. If you have good foundation in 8085, it becomes very good, or it helps you a lot when you are going for a more complex microcontrollers. Okay, because these are all correlated in one or the other way. So 4 clocks. If you remember, in that it was suppose like this: 1, 2, 3, 4 clocks, and the clock is running out, right? So here, from here to up to here, you have the clock. And you remember, opcode fetch, we used to draw something like this, right? Something like this, and then a small line was there in this region. You remember or not?
Yes,
Yes,
sir.
sir.
In some instructions it used to be longer, whereas in some instruction this particular time used to be smaller, and this line used to be longer. But still, in every case, what was the size of the clocks? 4 clocks. So this kind of scenario, when we are taking, like you said, yes, some instructions may take more time to decode. For example, multiply, of course, will take more time than just addition. Or maybe right shift or left shift will take less time than moving a data from memory to register or register to memory. But in any case, what they will do, they will take the largest time period, okay, for for any particular instruction, and they will say, okay, we will always dedicate 4 clocks, right, for every instruction, be it a small instruction or a large instruction. What does that mean? It means whether it is taking more time or a smaller time, the maximum time we know for any opcode to be fetched is 4 clock. So let it be there for 4 clock. Don't change it according to one instruction to another instruction. Let it be always 4 clock. Similarly, this time will be fixed on that basis. Okay, the maximum time taken by any of these three term, whether it is fetching, decoding, or execution, they will take the maximum time period, and they will say, okay, this will be the always the same slot, whether it is taking a small time period or a larger time period, let it be always there. Because that is dynamic, like you said. Yes, it is dynamic. It is not always static, that all the instructions will not take same time to decode, or maybe also all the instructions will not take the same time to execute. Got it? So the easiest way is take the the the, the largest time taking event and distribute this particular time for that period only. let it go in that fashion. Okay, got it?
Yes, sir.
This is one simple way. Might be possible they are having more complex algorithms nowadays, but this is the approach. Okay, now coming to the benefits of pipelining. What is the benefit? Of course, you can do multiple tasks and it can be completed in a very small time period. Okay, it improves the overall throughput. What is this meaning of throughput? Have you heard of this word throughput?
Yes, sir.
what, what is the
Yes.
meaning of throughput?
Sir, data transfer per unit time.
No, it is not always data transfer. Okay, one of the term maybe data transfer. Other than that, what is throughput?
Bits.
No, anyone else? Bits also, but what is throughput? Remember, throughput is a common word which is used to say the performance. Okay, whenever you are saying speed, so throughput has increased, that means more number of instructions have been completed in one small time period. If you are saying, like you said, if it is the communication based system, throughput, higher throughput means higher data rate. So this word is not a fixed word for a particular thing. It is more technical word which is used to say that okay, the overall performance of the system has increased. The performance of a system may vary from one system to another system. For example, if I take an example of a motorcycle, the performance of a motorcycle can be divided into so many ways, like speed of the motorcycle, right? Average of the motorcycle, or maybe braking specific brakes or something like that, right? So there are so many performance parameter which can be checked. So if you are saying throughput, it always you have to ask the person on which parameter you are talking about. Okay, so here the overall throughput of the system increases, that means overall speed of the system increases. Okay, like the question was raised before, different blocks in the pipeline can have different execution speeds, like fetching, decoding, and execution may have different speed. Okay, so depends, so it is not always constant. The pipelining length increases, this total time period increases depending on the amount of work done by each state is reduced. Okay, so if you are, this is the trade-off you can say. Okay, so if you have a better processor, it will have better operating frequencies. Okay, this sentence is a bit confusing. Anyway, you can say it is having more speed overall. Now, important thing to remember is the 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 newer ARM Cortex or ARM processors like ARM 9, ARM 10, they use longer pipelining. Like ARM 9 uses 5-stage pipelining. ARM 10 uses 6-stage pipelining. In 3-stage pipelining, you were having fetch, decode, okay, and then you were having execution. Okay, whereas 6-stage pipeline will have more number of stages and it will introduce some more terms. For example, let me just briefly go and check what are the other things which are there in pipelining. So 6-stage pipeline. Okay, what are there in 6-stage pipelines? Okay, here you have, wait, ARM 6-stage pipelining. So here we have three stage. This one's okay. Here we have fetch, decode, execute, memory, ls, memory write. So in this way, they keep on increasing the number of stages. Okay, so we don't have to look into that part because we are going to use ARM Cortex M4. So M4 uses 3-stage pipeline. You can go and check what are the other blocks which are introduced when you are going for 6-stage pipeline. I had that image with me, but I think I have not put that in the presentation. Anyway, So remember, it is not that the 3-stage pipeline is the most efficient pipelining. There are 5 and 6-stage pipelines also. And there are also, for example, it is not necessary that 6-stage pipeline, for example, what I mean by this statement is, it is not that sometimes there are instructions which don't need to do execution at that very particular time. They might be using some branching instruction or some other instructions. So this kind of stage pipelining does not mean always you will have all the tasks in one particular slot. Sometimes some of the tasks are also missing, but still 6-stage pipelining means normally there will be 6 stages for completion of any particular instruction. Okay. So of course the trade-off is between complex hardware resources. So of course you have the faster speed of execution, but you will have to pay for more complex hardware resources. Okay, before moving ahead, let us just briefly go through these things, because this will help us to check whether we are following the class or not. What is the base address of GPIO B register? Tell me. You open the datasheet and let me know if you can find the answers for this kind of questions. What is the base address of GPIO B register? Please open the datasheet and let me know the address. Anyone? Base address of, please start checking from your side, so that you should practice this part also, okay, so that you become more and more familiar with the data sheet. Okay, so how to access the memory? Let me briefly tell you about the data sheet. Okay, here I have the data sheet. Can you see the data sheet now?
Yes, sir.
Okay, here in this data sheet, in the left side you can see there is all a listing of the chapters and all, right? So it is a very big document. It takes somewhere on 1400 pages. Yeah, 1409 pages. So it is not possible that you can always go through all the pages. It is not possible at all. So whenever someone is asking anything regarding the data sheet or any particular peripheral or clock or memory, first go through the index which is provided here in the left. Okay, whether you are using Foxit or any other software. In this, for example, now the question here is simply, the question was regarding the base address of GPIO B register. So first of all, we will go to the GPIO section. For that, we can go here, go down and see GPIOs, right? So click that first arrow of plus sign and you open this particular section. In this section, what are the things which are important? You can see here in this section you have signal description, functional diagram, initialization and configuration, register map, register descriptions. Okay, so of course we'll need the detail regarding the register. So click on the register map. Okay, done, and we jump to this particular page where we have the register map for GPIO. Clear? Scroll down and check what are the pages here. The first information is about the GPIO port A, APB 4000 4000. Scroll down, you can see GPIO B, APB 4000 5000. Second GPIO B, AHB 4005 9000. Got it? Please follow the data sheet so that you can practice it along with me. Okay, so when I'm showing you this thing, please follow this along with that. Otherwise, it will take very long time to write a program for ARM or any other microcontroller. So here you have the addresses. Now, what is the answer here in that case? What is the base address of GPIO B? Base address of GPIO B is
4,000.
4,000,
4,000, 5,000.
4,000, 5,000. Remember. Okay. So now there is one more question here, because GPIO B, one is along with APB, the other one is with AHB, right? So APB and AHB, we will come to that also later, don't worry. These are two different types of buses. APB, advanced peripheral bus, AHB, advanced high performance bus. So in general, we talk about this particular line, and if you need very high speed data communication between the ports or microcontroller, you or the GPU, not the GPU, the ALU, sorry. In that case, you will be using AHB. I will show you the bus. When we will talking about the bus architecture, we will explore more about that. Anyway, so the base address is, you can say 4,000, 5,000, or you can even say 4,005, 9,000. This is the base address. Let me go back and tell you again how to search the datasheet. Open the datasheet. In the left side, you have all the details regarding different peripherals, memories, and all those stuffs. So when I am asking you a question regarding GPIO, or anyone asks you about GPIO, go to that section, click on that, register map. If you are interested in the addresses, go to the register map, scroll down, you will see the addresses of the different GPIOs. Okay, clear. So done. So base address for port B is 4,000, 5,000, or you can even say 4,005, 9,000. First question has been answered. Next, what is the base address of flash memory? How you will search that? Base address of flash memory. Anyone?
4,000 F D00.
No. Don't jump into the directly to the answer. Tell the
Internal
process.
memory. Internal memory.
Okay, so you are interested in the internal memory. You open that section, then
Flash
register
memory.
map. Register map, right?
No, sir. Flash memory register.
Okay, this one. But here, where? This one? Descriptions.
Yes, sir. Here base address is given now.
Okay, this one you are saying.
Right. Base address is given here. Down. Flash memory address.
This one, 4,000 F D000. Okay, otherwise you can first go to the register map. Okay, don't jump directly to that part. Okay, always first check the register map, what is there. Okay, so in the register map, you here also you can see the flash memory starts from 00000000. Got it? That part, when you are seeing this part, flash memory description. Okay, description means to control the things. Don't go into that part. Okay, right now don't go jump into that part. I will come to that part. Okay, don't worry. So register map. Okay, if suppose someone is asking you about the flash memory address, you can see starts from 00000000. But no, this is not the base address. The base address is 4,000 FD00. Yeah, clear here. Okay, flash memory control base. This is this one, right? Okay, done. Third question is related to the watchdog timers range of address. Range of address for watchdog timer. So base address is different, range of address is different. That means range means from minimum to maximum address which are allocated to watchdog timer 2. So watchdog timer 2. Now the question is regarding watchdog timer 2 and the range. So minimize this, go to the watchdog timer section, then go to the register map, and here you can see the base address, that is 4,000 for watchdog timer 0, and watchdog timer 1 is 4,000 1,000. But range, if suppose someone is asking you the range, then what will be the answer in that case? What will be the range of address for watchdog timer. So for that, what you can do is first come to the internal memory and let us check if we can find the watchdog timers range. Otherwise, not here. So system, wait.
Sir, number 12.
Yeah, I opened that part. Number 12 and register map, right? We are interested in the range. So FFC is the last, okay? FFC is the last register. Here you can see FFC is the last register. Apart from that, if you want to directly know the range, you can go to, let me check here, register map. Here we have, let us check watchdog timer peripheral. Here it is not talking about all the range. The previous class I showed you about the range. Let me show you again. Register map here. Watchdog timer. Go down, MPU floating, right. Memory model. Yeah, this memory map. Here you can see all the range. For example, watchdog timer. Here you see in this page, peripherals. So watchdog timer's range of address for watchdog timer 0 is 4000 to 4000 FFF. How we got that? We directly went to the memory model from the processor. For example, here chapter number 2. In this, there is one table which shows everything about the memories. So here you go to this particular Cortex M4 processor, go to the memory model. In that, you come down to the table, this table, okay? And then here you can see the memory model, memory map. In memory map, we can see what are the ranges of each and every individual peripheral. For example, watchdog timer, the range of address for watchdog timer 0 is 4000 to 4000 FFF. Watchdog timer 1, 4000 1000 to 4001 FFF. So this is the range, okay? Similarly, now the next question was related to the range of address for ADC 0 and ADC 1. Okay, no issues. So scroll down in the same page, scroll down and you can see ADC 0 here, 4003 8000 to 4003 8FFF. This is for ADC 0. Similarly, ADC 1, you have 4003 9000 to 4003 9FFF. Okay, so this is the range. Please note these numbers. Just note these numbers. We can go to these numbers in alternate way also. There is an alternate way to reach to these numbers. Like I told you, go to this section. If you are not always interested to open the microcontroller's whole memory map, come down. Here you can see ADC, right? Click on that, come down, register map, right? So you can see the starting address 4003 8000, right? And we also know that each peripheral is provided somewhere around 4K of memory. Otherwise, you can scroll down, see the starting address, start from 000. This is the offset, okay? And you come down, and here you have 4C FC8 onwards. So it is basically FFF, okay? It goes up to FFFF. That's all, okay? So this is the way you can check. One is go to the peripheral, open the register map, or the other way is go to the microcontrollers and then open the memory model. This way you can check the range. Now, one thing that helps to analyze this data sheet, let me show you one important thing. Okay, these are all peripherals. If you see here, GPIO is a peripheral, general purpose timer is a peripheral, watchdog timer, ADC, UART, SSI, I2C, CAN, these are all peripherals here. Yet from chapter number 10 onwards up to chapter number 21, right? From chapter number 10 to chapter number 21, you have all the peripherals. And if you open these things, if you see here, one very common thing you can find. What is that? One is the signal description. Then after that, functional description, initialization and configuration, register map, and register description. So these 5 terms will be almost common for each and every peripheral. You check it here. So it will be very easy for an engineer if he understand the way to read the data sheet. It is not possible you keep on changing the pages and keep on searching the things. So if you are interested in initialization and configuration, first of all, signal description. So what are the signals required to activate, deactivate the thing or this particular block? Then after that, you have initialization. For example, here. So what does that section will tell you about that particular thing? For example, initialization, how you can configure or activate or change the behavior of that particular device. Okay, for example, here, in case of initialization for GPIO, these are the steps to be followed. 1, 2, 3, 4, 5, 6, 7, 8. Okay, these 8 steps, if you follow them, you can configure the GPIO in many ways. Similarly, if you are interested in the timer, so go to this particular section, initialization, and then you can check what are the steps to be followed. For example, if you want to push the timer into one-shot timer mode, this is one mode. Okay, 11.4.1, go down, it takes 8 steps. Otherwise, if you want to go for real clock mode, 11.4.2, similar 7 steps. Input edge count mode, input edge timer mode, time mode, PWM mode, and so on. So instead of by hurting the thing, can you tell me how many different modes are there in the timer? By just looking in this particular data sheet, how many modes are there in the timer? Take your time, because it takes, this is what the embedded engineer do in 80% of the time, going through the data sheet and then writing a code, coming back to the data sheet, writing one more line. So in this way, they master this particular subject. How many modes are there in this microcontroller timer?
5.
5 modes. Simply 11.4.1. So 4.1, 2, 3, 4, 5. 5 modes are there. And if you want to know more about the modes or what are the things there in those modes, you can go and study about this part. Okay, what the timer can do and all those stuffs. Okay, what are the different modes and when you should use which kind of mode. Okay, for that you can go and thoroughly study about this particular timer's behavior for here. Okay, clear? This is how one person masters that particular microcontroller. It is not necessary that you will be someone might be using a timer for his system or a project. Someone might not be interested in timers. Someone might be interested in watchdog timers. He will use this section. He will follow the register map of the watchdog timer and he will try to understand this particular descriptions, register description, what these registers can do. We will follow this. Okay, anyway. So we have answered all these questions, sorry. So all these questions are clear. So anyone having any difficulty how you can find the base address or the range of any peripheral from the data sheet? Anyone having any difficulty now? I don't want to go too fast in this part because this is what the core essence of this particular subject is. Data sheet and understanding the proper way to approach it. Anyone having any difficulty? Anyone? So, okay, someone might say, sir, you are talking about TI microcontroller, so it might be very easy. So let us go and STM32 F FR44, wait, F446RE datasheet. Let us download this datasheet also. And let us see how the ARM, STM company is providing their datasheet. And so that you can understand how to approach them. No, I will not go for the datasheet in this case. I will go for the reference manual. Okay, reference manual here. Download this. Go to the address. Open it. It will be much bigger. So you can see here again the manual is 1347 pages. It is not possible for anyone to go through all these things. But here again you see the structure they are following, almost the same. Let me show you here also. GPIO. These are all, see, all the peripherals, ADC, DAC, digital camera interface, general purpose timers, and then basic timers, and all those things are there. So if I click on this particular part, you see introduction, main feature, functional description, and GPIO registers. Click on that. So what here? Come scroll. This is there. So here you see GPIO registers detail. Same, almost same way to see the data sheet. So don't have to worry about whether you are studying STM microcontroller or TI based microcontroller or something. If I close this, go up, memory bus and architecture. So memory organization, see here, same, you will get all the details regarding the peripherals. Otherwise, if you start from zero, it will be very difficult. See here, they are representing the same thing in a different way. Got it? Anyone having any difficulty now to whether you choose a STM microcontroller or any other microcontroller? You should be able to know these things. Okay, so always go through this particular data sheets, and this is the way to look into the data sheets. Okay, now let us go back to the lecture here. Okay, I'm not going to go through all the slides here because most of the time I will be uploading separate video in the YouTube. Okay, so I will be discussing some of the more important things in the classroom. Rest, C programming and all, I believe most of you already know the basics. If not, you can follow the YouTube channel. I will be posting videos regarding this subject. Okay, so first of all, I believe most of you might not be knowing about Big Endian and Little Endian system, or anyone who knows Big Endian and Little Endian system. Have you heard of Endian system?
No, sir.
No, sir.
Okay, so different companies, different microcontroller manufacturers follow different Endian system. What does that mean? Endian system. Endian system means how you look to the data, the way you look the data. For example, Endianness is the term that describes the order in which the sequence of bytes are stored in the computer. The way you look into the data, I can say. Okay, for example, assume we have to load a data 0x1234567. This is the 32-bit data, and I want to load this into the memory. And we all know that this is the MSB part or number, or this is the LSB number, right? This is MSB number and this is the LSB of the number. Clear? Let us see what is Endianness and how different companies use different approaches. So Big Endian system, if the company is following Big Endian system, he will be loading or unloading the data in this particular fashion. So you have the memory here. So lower memory is here 2000, 1001. Higher address is 2000, 1004. So the address is growing up in this way. Okay. So the memory is growing up. So the data, if you are loading this data into a Big Endian system, you can see 67 has moved to the higher address. So 67 goes to higher address. Whereas 01 has moved to lower address. So MSB goes to the lower address, whereas LSB goes to the higher address. This is what big Endian system follows. Whereas little Endian system, what they do, they take the same data, okay, and again here you can see the memory is growing in the upward direction, okay. Now the higher address always gets the MSB and the lower address gets the LSB. Okay, so this is the difference here. So here you can see 67 goes to 04, whereas 01 was loaded to 01. So MSB was loaded to lower address, LSB was loaded to higher address. So it is kind of cross. Whereas in case of little Endian, higher address gets the MSB, lower address gets the LSB. So it is very important when you are writing any program or any embedded system or any computer related software, you must know how the memory is or which memory is getting which data. Otherwise, we will be making some mistakes. So remember ARM Cortex M4, we are using M4. They use little Endian system by default, but we can change that if needed. Okay, it is not necessary. You always have to follow, but by default, little Endian system is used, and we are familiar with this approach. We always look into the data. Higher data is loaded to higher address. Okay, but are there any companies which are still using big Endian system? Yes, many companies are using big Endian, like Atmel, Motorola, Xilinx. For example, Xilinx you might be using in the VLSI, right? So if you are following Xilinx board or something, they use big Endian system. Okay, little Endian system like ARM, one of the example is ARM Cortex M4. Indeed, apart from that, Intel's x86 and x64. x86 means 32-bit systems and x64 means 64-bit system. Even your latest Intel i7 and i5, they are using little Endian system. Apart from that, Zilog is one other microcontroller or microprocessor manufacturing company. They uses little Endian. So this is very important to understand, because when you are going through the memory and decoding the data in the memory, many a times people get confused why the stack is following this particular approach and memory is following this approach. So you have to have the knowledge of the Endianness of the system. For example, that you can even get this information from the data sheet. For example, Endian. If you type here, let us check the data sheet gets that detail. Okay, remember we will be following little Endian system. I will show you that also when we will be uploading the program. Okay, where is that Endian? No, what happened? Yeah, see here, data storage. So, please, these are very important. Data is stored in little Endian format. Clear? So this is again very important feature, and many a times these kind of questions are asked in the interviews also. These are the core things which a person should know. Apart from that, we all know about signed and unsigned number. For any signed system, one bit will be dedicated for the sign, that is always the MSB. Okay, that will be your sign bit. Okay, clear? If you are using a sign bit, and that we all know how to convert a number into signed bit and signed number. You take 2's complement and then do all the mathematics. We have discussed it in the previous lecture, so I don't want to put time in this. Okay, these are, but anyway, if you want, then you can follow this slide. Okay, I have mentioned every steps. I don't want to put time in this. Okay, anyway, next, floating point unit. This is very important. We must know what are the different types of floating point units available in the microcontroller or microprocessor. First of all, there are 32-bit instructions. If you are using 32-bit instructions, we call it single precision floating data. Okay, and generally multiplication and all, okay, leave it. They use Mac and all, leave it. We will come to that part. So FPU supports almost all the instructions like converting a data type, adding a data, subtraction, multiplication, division, square root. This particular FPU, I told you it has got 65 instructions. Okay, they support all these kind of mathematics, which are generally used for normal numbers also. So FPU is able to handle addition, subtraction, multiplication of floating numbers. Okay, it is not that always you have to use real numbers, you can use floating numbers also. Okay, so IEEE came up with some mathematical formula to get into the floating numbers. Okay, so if we have 32-bit system, then we will call it single precision registers. Okay, and then we have, okay, leave it, decoupled 3 stages. It supports 3-stage pipeline. So now the question is, um, how a computer converts a number, a floating number, into its hexadecimal equivalent. Okay, without using decimal point there. It is not that you will have 0x3 to f dot, okay, dot to a c d. No, it is not allowed. It is not allowed in the memory. Dot is not there. We don't have a special character like dot in the memory. So always all the data which will be loaded will be a normal number like 32 f a b c d, something like that, hexadecimal. It will not have dot in the memory. So how to do that conversion? So IEEE, you might have heard about IEEE, came up with this particular protocol 754, which allowed us to convert normal numbers into floating point numbers, because modern computers, they support floating point standards. So because more and more complex mathematics were dealt with these modern computers, they had to come up with a system which can support floating point numbers. So there are basically 2 floating point standards which are approved under IEEE 754. Okay, and still most of the computers are following that. So one is called 32-bit single precision floating point system. Second one is 64-bit double precision floating point number. Okay, so 32-bit single precision, 64-bit double precision. What are these two number systems? So first, in a single precision system, they will be using 32 bits. So B0 to B31. One bit will be dedicated for the sign, whether you use single precision or double precision. Okay, just put some text. If you need, you can take a 2-minute break, because this is you have to focus here. Okay, you have to focus here to understand the mathematics, because it is very important. And if you are good in this part, you can do more complex mathematics, and you can understand the microcontroller in more depth. Okay, so basically there are 2 systems, 32-bit and 64-bit. 32-bit system is called single precision, 64-bit is known as double precision. In both cases, 1 bit is dedicated for sign. In single precision, it is a 32-bit system, so you have bit 0 to bit 31. Double precision is 64-bit, right? So you have B0 to B63. Done. 1 bit is gone for the sign. Rest. In single precision system, bit number 30 to 23, that are 8 bits, which are dedicated for exponent. We will see the mathematics. Okay, and bit number 22 to B0, which are 23 bits, are dedicated for mantissa. Similarly, in a 64-bit double precision system, 11 bits are dedicated for exponent, and 52 bits are dedicated for mantissa. So now the question is, what is exponent and mantissa, and how to get those numbers? Okay, or how to fill these particular gaps. So please make note of this system. Okay, sign bit, exponent, mantissa. 8-bit, 23-bit, 11-bit, 52-bit. How to get these bits? Okay, clear. So I have just put them here. Okay, so for any n bit number, 1 bit is required for the sign. M bits are required for mantissa, M for mantissa. Okay, M bits are required for mantissa, and E representing exponent. Okay, E bits are representing exponent. Okay, so this is all about right now the definition. Okay, now what is the mathematics behind it? How the floating number is converted to its equivalent uh, uh, floating number system. Okay, okay. So first, let us talk about a 32-bit system, which is single precision floating point number. Okay, so first number I told you 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa. So in total, if you calculate this, 32 bits. Okay, let's go ahead. Example, suppose we have a number 45.25. Okay, suppose you just declared a number, a variable like float deep, okay, is equal to 45.25. So what is this number? What is the actual hexadecimal equivalent of this number, which is stored into a 32-bit number? Okay, so that is what we are going to decode here. Clear? So now, first we have two sections. One is 45, second is 25. This is after the decimal point and this is before the decimal point. Okay, so first of all, we will convert the 45 to its equivalent binary number. You know how to convert that. Divide it by 2 and you will get this particular number. Okay, done. Then second, you have 25.25. Okay, you have to convert it its equivalent binary, but remember you have to go up to 23 digits. Why 23 digits? This will go to the mantissa part. Okay, so even though you have zeros here, keep it up to 23. So these are going up to 23 bit positions. Clear? Now, so now we have this number which is representing 45 and this number which is representing .25. Okay. Third step. So 45.25 we have arranged it in this particular fashion. 23 bits here, and this was the equivalent for 43. So done. Now remember here you have the dot decimal point in this point. Okay. Now the question is how many times you have shifted this dot to reach before the MSB. So 1, 2, 3, 4, 5. So you moved the dot 5 times to reach here at this point. Make a note of that. Okay, so 5. Now, so what does that mean? First of all, to get the base exponent function, okay, biased exponent function or the number, we have to do a small mathematics. What is the mathematics? First, it is 127 plus 5. Why 5? Because you moved the decimal point 5 places to reach to the before the MSB, just before the MSB. That is 5. Now the question is 127. How you got the 127? Here you see you have 8-bit you have dedicated for the bias. So what you do here, 2 to the power bias exponent minus 1. So 2 to the power 8 minus 1. This is one part. Then after that minus 1. This will give you 2 to the power 7 minus 1. 128 minus 1, you will get 127. Got it? So you have now 127 plus 5. You will get 132. Okay. So clear up to this part? Anyone having any difficulty up to this part? How gradually we started moving from 45.25, and how we reached to this particular number 132.
सर एक बार फिर से बता दीजिए.
Okay, simple. 45 and 25. Okay, so you segregated these two numbers. It might be possible you might have received 2, 5, 6, 8. Right? It is not that always you go for floating number. Is this also? This one is also a floating number. So now here you have 4 numbers and 2 numbers here, or it might be possible 145. So first job is to convert this 145 and 2568 into their equivalent binary numbers. And this mathematics we know from the first year or maybe from the digital electronics. So convert the 145, you get a bit sequence. Second, this number after the decimal point, convert it to equivalent binary number up to 23 digits. Now the question comes, why 23 digits? Because these 23 digits are for the mantissa. So after the decimal point, this is the decimal points after the 6. This will go and represent the mantissa. Okay, and that is according to IEEE 754. There should be 23 digits dedicated for mantissa part. Done. So you got these two numbers and you arrange them in this fashion. Normally just the number dot this number. You arranged it. Now the question is, this dot, you have to count how many number of times you have to shift this dot to reach just before the MSB. So you count it. Here it was 45, so we got this much. So 1, 2, 3, 4, 5. So here is the decimal point. So 5. So 5 is here. Okay. So that 5 is here. Now the question is how to get this particular number 127. There are 8 bits dedicated for biased exponent. So you follow this equation 2 to the power. Okay. 2 to the power 8 minus 1 minus 1. Okay, it will be always, because this is always going to be 127. So you don't have to worry about that part. So it will be always 127 for 8-bit biased exponent. So 127 plus 5, which was the movement of the decimal point. Then you got a number 132 up to this. Then after that, you convert the 132 to its equivalent binary form. So you got it 10000100. So now you have almost finished this part. So normalizing the mantissa, that means removing the dot from this mantissa. What you are doing? So you are removing the dot. So let us see here. You see here, we are moving from here 0, 1, this, and you are going up to this number. Okay, this is normalization. Okay, so here you see this number has been transferred to this part. Clear? So 0, 1, 1, 0. Then after that 1, 0, 1, 0. Then after that all zeros. Clear? This you have done. So this is normalizing the mantissa, because you have shifted the dot to that just before the MSB point. Now you have 132's equivalent and the mantissa. Okay, you combine them. Why the 0 has appeared here? This is the sign bit. Why the 0? Because this number is positive first. So 1 bit for the sign. So 0 for positive number, 1 to represent negative number. Okay, positive, negative. So because 45 is positive here, this number is positive, you dedicated 1 bit 0 for the representing positive number. Now after that, this 132 has been shifted to this number after the 0, and then the normalized mantissa has been moved. So now if you check here, you will get the complete number. Okay, and you will now frame it in sections of 4, because you have to convert it to hexadecimal. So 0, 1, 0, 0, 4, 2, 3, 5. Or you can get to this particular number. Okay, I think somewhere I have made a mistake here. 4 to this should be 4 through 2. 4 2 3 5 0. Okay, 4 2 3 5 0. Okay, 5 0. This will be the actual number. Clear? This is how you get the equivalent of this number. Is I have made it wrong here. Okay, so 4 2 3 5 0 0 0 0 is the actual conversion of 45.25, and this will be stored in the memory. Okay, 45.25. Okay, do one thing. You can practice it when you are uploading a number into the code block. Check what is loaded into the memory also. Okay, this way you can practice. So now this is the way to go for the single bit or 32-bit system. Now double precision, in that you are using 64 bits, 1 bit for sign, 11 bit for exponent, and 52 bit for normalized mantissa. Same approach. You will not do anything more complex here. Okay, first convert the 45 binary, then 20.25 is converted to its binary, but remember up to 52 digits. Okay, then you arrange them like this dot this, right? You done that. Then after that again you count how many points you have moved to reach to this point. Again 5, because the example is same. Okay, so now 1023, you know that is 2 to the power 11 minus 1. Why the 11? 11 is from exponent. 11 minus 1 minus 1. So this will give you 1023. This will be always constant for 64 bit or double precision constant. Okay, so 1023 plus 5, that is 1028. Clear? And you will convert that 1028 to its equivalent binary format, and then of course you will have to normalize the mantissa. Okay, so it will become 0 1 0 like this, 0 1 1 0. Then after that 1 0 1 0. So 1 0 1 0. Then after that you have zeros, so all zeros. Clear? Normalization. Then after that join these two and put a sign bit. So because you have positive number, sign bit will be 0. You have the bias number and this, so arrange it in this fashion, you will get the final number. Okay, so here you have A. Yeah, correct. So this is done. So I am providing a link also in which you can practice if you want. Otherwise just have the common, don't have to by heart it, practice it 1 or 2 times. But just I was just trying to show you that how a floating number is stored in the memory of the microcontroller or a PC. So just imagine, it is so simple to say, okay, we are using a float, a variable name. So where one will be the variable name, and you can put a data here like 32.6828. So simple to say, but you see how many different mathematical instructions are going behind to convert such a number to its equivalent hexadecimal. This is what I wanted to show you. So there are so many things which are going at the background, which generally people don't talk about. But if you know these things, of course you can sit in an interview with more confidence. Okay, clear, done.
Excuse me, sir. सर सिंगल प्रिसिजन में 45 को पहले ही क्यों नहीं 8 बिट में लिख रहे थे, मतलब 2 0 आगे लगा के?
Why you write?
सर 8 बिट फॉर बायस्ड एक्सपोनेंट ऑलरेडी हमने असाइन किया हुआ है ना.
But I told you the steps. Now it is not. Go and check that if you get the same answer. I'm not going to. No, I'm not going to discuss that part here. If you practice it according to your choice, check it and check with the answer. If you get it, okay, no issues.
Okay,
Might be possible. Okay. I am right now I am, because look, when we are taking a lecture, right, and for some conditions some of the mathematical equations automatically fits, but suddenly in some other conditions they don't fit, and then the student will come to me and say, sir, aapne to bola tha this was okay, and now you are deducting my mark. So right now I cannot no think out of this particular approach. You are saying
ओके सर।
45, you are saying 45.
सर 6 बिट का आपने नंबर लिया ना, मतलब 2 जीरो आगे और डाल दो, मतलब वो 8 बिट का पहले से ही हो जाएगा ना, क्योंकि हमने बायस एक्सपोनेंट के लिए 8 बिट असाइन किया हुआ है।
I don't know. Cross check it. You are saying that you just put 0 0
हाँ,
1 0
यस
1 1 0 1.
यस
This one. Then
यस
how you will get 5 here?
सर। सर ये स्टेप तो सर ठीक है, मतलब मुझे लगा क्योंकि 23 बिट हम
No,
कर
I
रहे हैं
got
इसमें।
no. 23 bit is for Mantissa.
हाँ, मतलब
After
इस
20,
प्रोसेस में
this
23 बिट हम यूज कर रहे हैं मिंटिसा के लिए, बट 8 बिट मतलब अलग तरीके से निकाल रहे हैं तो।
might be, I don't know, but here that I'm not sure you will be reaching here correctly or not if you follow this approach.
ओके सर।
Because this if you are going to count this as a MSB, then in that case 1 2 3 4 5 6 7 stages you will get, and here it will become 7, right?
ओके
So
सर।
and anyway, we don't put zeros in the front of any binary number. It does not make any sense, does it? Yeah, if you are saying it is a 8 bit, okay, so you are saying, okay, you are saying this to be like this 1101. So
यस
now this whole number makes a different 20, what, 20b, 2b,
2 बी।
something. No, not b. 841. So 12 13 a b c, d, maybe d. So I'm not sure. I'm not sure. Right now, I don't think you should put zeros before the 45. Okay,
ओके
these
सर।
numbers. Avoid. Anyway, so this is what IEEE 754 talks about. And in short, if you don't remember these steps also, don't worry. But you must know that how 32-bit system and the 64-bit system stores the number. And in my example, in my video lecture, in the about the, I showed you this part also, I think. Wait, code block, and there is, because of that, there will be always an error also. You will never get precisely the same um floating number in the memory. I will show you that part also. Let me just briefly take any example like this. Okay. Okay, for example, I will declare a float here. Float d equal to 23.456. Okay, this is what we are saying. And then okay, this much. Compile. So let me check whether I am compiling test1. So I will block this part, disable test1, I will enable. Okay, so this program we are going to check. I have talked about all these windows in the video lecture, okay, which I have loaded in the YouTube. Anyway, so here you can see, okay, so here you can see the program is waiting here. So this line has not been executed. So right now there is a variable deep for which the compiler has allocated a memory, and in that there is a garbage value which is 5.87. This is not the actual value, because right now it is a garbage value, like a, b, and all these are getting some values, whereas we have not defined anything, because a is 15, but here a is 0, or a is this number, which is not correct. So let us check what will be loaded in this particular deep variable after executing this line. So let us go a step down, and you see here we have mentioned 2 3 4 5 6, right? 2 3 4 5 6. But in the memory, you see what has been uploaded. 234559994. Why so? And if I go to this address of deep, for example, if I go to the address of deep, address of DWP deep, I want to know the address. So this is the address 61FF1C. Can you correlate this? Right now, there is a variable. I'm trying to go to that variable's address. For that, I decoded the address here, and I will go to the memory window, and I will put that address here. So here, this is the data which is stored in the memory up to this part. Okay. So please go and check whether it is going to give you the same number or not. So this is the number E3A5BB410CFF61. Then after that 881240. This is what is this particular number 23456. So it has converted into a hexadecimal array or number. Okay. But how he is converting that? Even that might not be the correct value which is stored for 23456, because you can see here 23456, and in the memory it is storing 234559994. Understood? So
Yes, sir.
there will be always an error whenever you convert a hexadecimal number to its equivalent. So the links which I have provided here, for example, this link, okay, go to that link and check. They will give you the error percentage of error also. Okay, so for example, if you go to this link, this is decimal. Can I take 64? Okay, let me try 23.45. Okay, convert to binary hexadecimal. So this is the detail. No, apart from that error, they are not showing. Let us go to the previous slide. In that, I believe they have the details regarding the error also. Let me check this one. So this all takes a lot of time. So don't worry. Okay, 45.56. Okay, enter. Now here it shows error due to conversion. You see here. So anyway, you don't have to go in that part. Okay.
Okay,
So,
sir.
but you must know what is single precision floating point, double precision floating point. Whenever you are talking about 32-bit system or 64-bit system, how they actually handle the floating numbers, because FPU, floating point unit, is a dedicated unit in the ARM Cortex M4.